Hello everyone, my name is Evandro Miguel Teixeira. I'm from Brazil. I will present the paper Query-Based Metrics for Evaluating and Comparing Document Schemas. The outline of presentation is number 1, Introduction, number 2, Background, number 3, Query-Based Metrics, number 4, Experiments, 5, Related Work, and finally Conclusions. Let's start with the introduction. Relational databases, or RDB, are widely used to store data of several types of applications. However, they do not meet all requirements imposed by modern applications that handle structured, semi-structured, and unstructured data. In these scenarios, NoSQL document stores emerged as an option. They differ from RDB in terms of architecture, data model, and query language. As RDB and NoSQL document stores will be used together for a long period of time, it's necessary to investigate strategies to convert and migrate schema and data between them. Different approaches have been presented to convert the databases. Some of them consider just the structure of the RDB in the conversion process, while others also consider the access pattern of the application. However, none of the approach is concerned with the evaluation and the comparison of the output document structure against the existing queries that need to be adapted and then executed. So, how to decide which is the best document structure for the application? In this sense, in this paper, we present a set of query-based metrics to evaluate a NoSQL document structure that we call a schema here, in relation to a set of queries that represent the application access patterns. Our approach uses DAGs, Direct Acyclic Graph, as abstraction to represent the queries and the document schemas. The metrics were validating scenario of conversion from RDB to NoSQL document. The results show that the proposed metrics are effective to assist in the selection of the appropriate document structure. Background. In a previous work, we created an approach to convert RDB to NoSQL nested models, specifically document and column family models. In this paper, the context is related to the conversion from RDB to NoSQL document model. Our approach uses a set of DAGs to capture the source RDB and the target NoSQL document structure, which is an abstraction used to represent a NoSQL schema. In this figure, we have an overview of the approach. In the step 1 here, the user creates a set of DAGs to specify the conversion from RDB entities to NoSQL entities. And in step 3, data migration, the set of DAGs is sent to Metamorphose, our data transformation framework that translate each DAG into commands to read data from the RDB, transform them, and persist in NoSQL format here. Okay. In this article, we are extending the approach by adding the step 2, this step here, with the components query as DAG and metrics. The objective is to evaluate the NoSQL schema before performing the data migration in step 3. Okay. This slide shows how we define a NoSQL schema using DAG. In the figure, you can see 4 DAGs composed of RDB entities and their relationship. So, in this figure, you can see the DAGs customers, orders, order lines, and inventory. Okay. Each DAG lists a set of RDB tables which are transformed into one NoSQL entity, representing document structure or NoSQL schema. Okay. A DAG is defined as G equal VE, where V is the set of tables of the RDB and E is the set of relationship between tables. Below the NoSQL schema, where each DAG is mapped to a NoSQL collection. So we can see here the DAGs customers, orders, order lines, and inventory. Okay, and the entities are nested as objects or arrays of embedded objects. So finally, we can define a NoSQL schema as S equal DAG1, DAG2 to DAG-N, where each DAG represents a collection of S, schema S. We also represent application queries as DAGs. The DAG aims to represent the query access pattern. A query is defined as Q equals VQ EQ, where VQ is a set of vertices representing the query tables, and DQ is a set of edges representing the join condition between query tables. We define two roles to convert an SQL select statement into a DAG. Subqueries and full outer join clause are not supported. So we have some examples here. In the example we can see the mapping between query and DAG. So a query with one table and a respective DAG, two tables and three tables. Okay. We have more information in the article about the definition of DAGs by queries. Query-based metrics. We define 6 metrics to measure the coverage that a NoSQL document schema has in relation to a set of queries. The metrics receive the NoSQL schema and query by parameter, represented as DAGs. The user can measure the coverage relative to a given schema collection or to all schema collections. The first two metrics are dir edge and all edge. They measure query edge coverage against the schema or collection edges. Path, subpath, and indirect path measure query path coverage against the schema or collection paths. To calculate the coverage for the entire schema, we define the max function, which calculates the metric for the query for each collection and schema, and return the highest value found. The last one, metric recalls, is a little different. It returns the smallest number of collections required to answer a given query. Here we present how to combine the metrics for measuring the overall coverage of a schema with respect to a set of input queries. We define two scores used to rank the input schemas: query score or Q score and schema score S score. Q score is calculated for a given metric and a given query. This score enables to set up weights to prioritize the importance of specific metrics. Here we can see the definition for the metrics, key score for the metrics dir edge, all edge, and recalls. So here the Q score is the same value returned by the matrix, as we can see here. For matrix path, subpath, and indirect path is a unique value and is namely as paths. So it returns the highest value among the three metrics, considering the depth of each path and additional weight. The weights WP, WSP, and WIP are used to set up a priority between path, subpath, and indirect path metrics. For example, the user can configure higher weights for path metrics and lower weights for subpath and indirect path, prioritizing schemas with greater path matching. Or the user can set the same weights for all the metrics. S score denotes the schema score for a given metric. So here you can see the definition of S score. S score is the sum of the key score values for all the queries. Each query key I has a specific weight Wi, where the sum of all Wi is equal to 1, normalized value. For recalls metric, the S score is a ratio between the number of queries and the number of collections required to answer them. A schema that answers all queries through only one collection has S score equal to 1. So the S score provides an overview of how well the schema fits the query set. And in this slide, we present an example of applying the matrix for a given schema and input queries. So the first step is creating the NoSQL schema as a set of DAGs. The second step is creating the queries as DAGs. Then calculate the matrix. The table shows 5 queries and respective coverage for the matrix. To calculate Q-score and S-score, the user must define the weights for the matrix and queries. We have implemented a tool that receives schema and queries and automatically calculates the matrix. Through this information of this table here, the user can identify which queries require more attention or are not covered by the schema. For example, query 3 here is not covered by the matrix paths, and query 5 needs to join two collections to answer it. Okay, so through the results, we can identify which queries require the most attention or not covered by the schema, and the goal here is to provide the user a methodology for evaluating the NoSQL schema using the proposed matrix. In addition, through this methodology, we can compare different schemas in relation to a given access pattern. Okay. Experiments. We run experiments to validate our query-based metrics in an RDB to NoSQL document conversion scenario. The experiment has 4 steps. Number 1, NoSQL schema generation. Number 2, input queries definition. Number 3, matrix result. And the number 4, query code and the fourth analysis. In the first step, NoSQL schema generation, we selected an input RDB consisting of 7 related tables. We select 4 approaches to convert RDB to NoSQL document from the literature, which have different conversion roles. Then we apply these roles and create one schema for each approach and set a label from A to D to then. So we can see the schemas in the picture, schema A, B, C, and D. As a result, our approaches are represented by the same format as DAGs, allowing to compare them objectively. In the next step, input queries definition, we selected 7 queries to evaluate the schemas. We show the queries in SQL and also as DAGs. As we can see in the table, we can see the SQL commands and the DAG paths. The queries have been chosen because they contain different access patterns. And the DAGs above were created according to the translation rules from section 3.1 of the paper. Matrix result. We calculate matrix for schemas A to D and queries 1 to 7. The tables below show the results. So we can see each table for each schema. We can see the key scores for path, dir edge, all edge, and recital matrix, and in the bottom of the table the field S score for each schema. Now let's go analyzing the results. Considering the paths coverage, schema C has the highest score, with S score equals 93% of coverage, as we can see in the table. This means C best matches the access pattern of the query set. On the other hand, schema B has the worst S score with 8% of coverage. With respect to the paths matrix, the schemas are ranked as follows: C, A, D, and B. For dir edge and all edge matrix, the schema C has the highest scores. This means that the schema entities are related according to the query access pattern. But on the other hand, schema B has the highest all edge score, same as schema C, but has the lowest dir edge score. It is because the entities of B are related according to the structure of the queries, but the direction of the relationship is inverted. So GearEdge and AllEdge provide an overview of the correspondence between schema and query entities. For HEC-COS metric, schema C again has the best result with the S-score equals 100%, as we can see in the table. This means that all queries are answered accessing a single collection. On the other hand, schema A has the lowest HEC-COS, where it is necessary to get documents from different collections to answer some queries. For example, queries 4, 5, and 6. Okay? So HEC-COS is an important metric that shows which schemas needed to join collections of documents to answer queries. And finally, this table shows the S-score for path, GearEdge, AllEdge, and HEC-COS metrics, and it can be used to rank the schemas. As the metrics are not independent of each other, a single S-score is not defined for the entire schema. The user must analyze each S-score per metric, in the selection process of the most suitable schema. As a result, in this experiment, schema C has the greatest coverage for all the input queries. The last step, query code and effort analysis. We also measured the impact on query code and effort for each schema. To do that, we first of all create 4 MongoDB databases, one database for each schema. Then we implement all the queries for each database using the MongoDB aggregation pipeline. So we count the numbers of lines of code, and the stages for to implement each queries for each database. Table below shows the results. We can see the lock and stage fields. And we can verify that schemas with higher paths and GearEdge score require less lines of code when implementing queries. And on the other hand, schemas with lower scores requires greater number of lines of code, as we can see for schema B in the table. These results confirm that the metrics can be related to the coding effort of the queries with respect to the lock measure. To summarize, the metrics proposed in this article are intended to evaluate and compare schema options before converting data from RDB to the NoSQL document. We have implemented a tool that receives schema and queries as parameters, represented as DAGs, and calculates metrics and scores. The results show that the metrics are an interesting starting point in the evaluation process and selection of the most appropriate NoSQL schema. Related work. Our work related to works that present approaches to define NoSQL schemas according to user-defined parameters, and the works that convert RDB to NoSQL nested models. However, these works do not provide means to evaluate the schema produced. Consider the utilization of metrics. Our work is related to the work 12 that define 11 structural metrics to evaluate NoSQL document schemas. Our work is partially inspired by it. However, our approach has a different purpose, which is to evaluate and compare NoSQL schemas based on queries that represent the application access pattern instead of evaluate only the schema structure. And finally, conclusions. We presented a solution to evaluate how adequate a NoSQL document schema is with respect to a set of queries representing the application access patterns. We define a set of query-based metrics which are calculated based on the input DAGs, queries, and schemas. The metrics enable to identify how the target document schema covers the input regional queries. We applied the metrics on a set of schemas produced by existing RDB to NoSQL transformation solutions. We executed all transformation scenarios to confirm that the metrics can be related to the code and effort of the queries with respect to the lock measure. As future work, we aim to extend the evaluation to integrate with cost-based approaches. Some references, and thank you very much.